Now we are going to see very quickly on application of linked list, one of the important applications of linked list, that is the representations of polynomial and addition of polynomials. So how to represent polynomial in terms of linked list and how to add two polynomials using linked list. So this is one of the prime applications of linked list that we have. So we all know what is polynomial. So polynomial, we can represent the polynomial as a function. Let's say fn is equal to 4x 4n cube plus 5n square plus n plus 1. So this is a polynomial, and in this polynomial, this is called, this 4 is called coefficient. All of you know this 4 is called coefficient, and this is coefficient, and this n this one is called power, or you can call it exponent. So we can also call it exponent. Okay, so exponent. So this is a representation of polynomial. So one is coefficient part, another one is exponent part. So higher the power, the exponent, the polynomial will be like, it will be, but if we increase too much, then it will be reaching towards exponential, which is non-polynomial it will become. So this exponent part is important. It should not go too much, otherwise calculating that polynomial will be a very cumbersome job and it will take a lot of time anyway. So coefficient part, power part, or the exponent part, and then the other one. So how to represent this in terms of a linked list? So let's say we have a linked list which is like this linked list node, and then let's say there is another linked list node which is this, and this is another. So in this case, let's say this part, this first part, actually you can represent this part as a coefficient, this part as an exponent or power, and this last cell will work as a pointer to the next node of the linked list. Similarly here also coefficient and then exponent, then this is again pointer. Okay, so this is how the linked list will be formulated, so that coefficient part, exponent part, that is the power part, and the link part of the, that means a pointer, this is nothing but a linked list pointer. This is a pointer which will point to the next node. Okay, like that. So initially it can be one head node can be here, one head node can be here, and then finally this can be grounded also, like that. So now this kind of linked list we can represent in terms of a structure. So structure is an abstract, it is an abstract data type because it can combine many things. It can combine variable, functions, etc. In C programming, and in object-oriented programming it is about class. Class also is an abstract data type. So first integer is a coefficient, and then power is that this part is the power that you can represent. This will be some number, power also will be some number. Let's say in this case it is 3, coefficient in this case it is 4, the first component of the this fn, and then last this one is, it is nothing but a pointer. This pointer will actually point to the next node. So next pointer is there. What is the type of this pointer? It is nothing but a node type pointer because our structure name is node type. And then we will be having a head pointer here. Okay, head pointer will be head pointer is nothing but a sentinel node. We have discussed it, right? So this is how the linked list will look like. So here you can see two polynomials are given. One polynomial is about a, which is 3x to the power 14, 2x to the power 8 plus 1, and another polynomial which is b, 8x to the power 14, and 3 minus 3x to the power 10, and then 10x to the power 6. Here it is 3, so this is coefficient part. Here it is exponent part of the power part. This is 14, and similarly this component, this is exponent 2, and this is the power is 8. Similarly in the last one x, it can be actually written as x to the power 0. That means 1 into x to the power 0. So 1 is the coefficient part and 0 is the exponent part, and then finally the here no pointer, further pointer will be there. So here is the next pointer, This is also the next pointer. Okay, similarly another polynomial you can represent like this, 8x to the power 14, but mind here it is minus 3, so here it is minus 3 plus minus 3 x to the power 10, so 10 comes here, and then this is 10, and then x to the power 6, and then null. Okay, so this is the next pointer. Okay, so these are two polynomials given, and they have been represented, visual representation of a linked list. So this is data part, this is data part, and this is the link part. Okay, so this we can represent easily with a linked list. We have seen that coefficient part, and then power, and then struct node type next. So next is a pointer. These you can write int power or int exponent exp also you can write it as usual. So you can write it exp here, no issue. So here instead of writing power, you can also write int uh, exponent. Okay, like that. Exponent and power both are same. So now when I'm going to add two polynomials which are nothing but 3x to the 3, uh, one second, let me just erase this thing. Okay, so here you can see that we have two polynomials which is 3 x to the power 14 plus 2x to the power 8 plus 1, and 8x to the power 14 minus 3x to the power 10 plus 10x to the power 6. So here three cases. Once you're going to uh, add this polynomial a and polynomial b, so polynomial a is here and polynomial b is here, and you're going to write c equal to a plus b. So representation you understood. Now let's say we are going to add these two polynomials, so c equal to a plus b. So in this case three cases will arise. First case is that if pointer p, let's say this pointer is pointing to the first node of the first linked list, we need actually two linked list, two linked list here. First linked list will be this one. So when you add it, so this pointer p exponent part, you can only add two polynomial, in this case 3x to the power 14, and in this case 4x to the power 14. Here the exponent parts are matching up. Here the exponent parts are matching up. That means 14 here, and here also 14. That means 14 here, here also 14. Then if this is the case, that means first part of the first polynomial, first part of the second polynomial, both exponent parts are matching. Then you can add the coefficient part. That means 3 plus 8 will be 11. So in this case, you can see here 11 has come. 3 plus 8 equal to 11. 11 has come, and then but because let's say this pointer is p pointer and this is the q pointer, so p its exponent part which is 14, q is another pointer for the another linked list whose exponent part is also 14. Both the exponent parts are matching up, so in that case you can add it, and you can have a new node which will be holding this additional value of the added value of the coefficient part of the first polynomial, and first part of the second polynomial, 3 plus 8 11. Okay, now this pointer, once this is done, then p will move to the next node and q will move to the next node. Pointers will come here again. So this is case one, which is one of the good case, actually best case. You can say that exponents are matching up, so you add the coefficient part, so 3 plus 8 11. And then in the second case, so p has come, q has come, but their exponent part is not matching up. So here you can see in case 2, so it is 8 is actually and sorry, this point, this node exponent part is p exponent is less than q exponent. Okay, p exponent which is 8 is less than q exponent which is 10. So if it is the case, then you copy this and put it here, and then you move your pointer q to the next node. Here if it is, let's say again case 3, p exponent, that means which is 8 is more than q exponent which is 6. So in that case you just copy this and put it here like that. So it will continue. And only thing thing is that whenever there is a, so it will copy in the final list. It will copy in the final list. So only thing is that when the exponent part will be matching up, then only they will be added. Okay. So this is how this polynomial list can be done.